Thanks very much. Thanks, Peter. Well, good afternoon, everybody. I'm delighted to be here this afternoon. And I suppose the idea here is it's a little bit of a curveball, so it's about concrete, but it's more about the evaluation of concrete in the hidden foundations under the turbines. So that's kind of what we're going to look at, the various different testing and investigation methods that we would use to reevaluate and hopefully to extend and reuse the turbine foundations. So we look at a bit about background, a little bit about condition assessment methodologies that we use, testing investigation techniques, and then a very short slide on the evaluation, interpretation evaluation of what we can find. So ultimately, the presentation looks at the principles and practices that we'll use in the condition monitoring. Typically, what we like to do is break it up into a phased approach. So initially, you'll have a phase one, a kind of preliminary, a look-see, see what we can see, what we can see on the top and the sides if they're available in foundations. And then we'll dig into the phase 2 and 3, which is more the examination, the techniques, the non-destructive testing methods that we use, partly destructive because we don't want to do too much damage to the foundations, and then the sampling, what the sampling can actually give us. And overall then it's the evaluation of the test results. So really what we would do is we'd try to break it down into various different phases, minimize the cost to the owners, but try to maximize the amount of information we get. So before we start, and one thing about wind farms, that in my experience, they tend to have a lot of information. So a desktop study and a structural history will be very beneficial. Design information in particular will be very useful. But most important at the bottom is the exposure class. That will give us as condition engineers an idea what the original foundation was designed for. Look at construction information. Do we have cube results? Do we have any other testing issues, curing issues, anything that might give us indication of what might be wrong? And then obviously if there's any defects or deterioration that was previously found on the turbine, be it shutters failing, be it chloride ingress, something that might give us an indication to look out for. But ultimately, it's about developing a technical plan. That technical plan will guide what we do going forward. So part 2 then would be in the appraisal, when we actually get to expose that concrete. So we've got an excavator in, we've opened up the foundation, or having a little look in the site inspection. Is it circular? Is it rectangular? Is it square? Sloped? What's the condition? Structural testing then that we might want to do. And if needed, we might look at putting sensors on the actual turbine foundation itself. But ultimately, it comes down to a well-targeted plan with well-trained people. And inevitably, because these foundations are hidden, we don't know what we're going to face into. So we have to have the equipment on site and the ability to actually kind of look into whatever we see. It'll often be an unknown process until we actually open up. And often something you're asked about, is there any guidance that's available? And there's lots of documentation available out there at the Institute of Structural Engineers, right down to manufacturers' technical guidance. But one particular very, very useful document if you are involved in structural testing and investigation or inspections is the Concrete Bridge Development Group's Guide to Testing and Monitoring. And one nice thing it has is it looks at the various different types of defects, typical structural defects you will have on exposed, heavily loaded structures, and then you have a series of testing and investigation that might be recommended. So, engineers are not going into this blind. They can actually see very, very quickly what they need to do. So if you have reinforcement corrosion due to chlorides, a 3 is essential. Obviously, visual inspection, cover surveys, delamination surveys, and just it's not absolutely definitive because I would be a heavy proponent on structure or petrographic examination. So I would add that in there as well. But ultimately, it's a really good guide to give you a very quick synopsis of what you should be looking to do when you open these foundations, just to stop you going in blind. So as we move on then, we'll move into the testing and investigation. I try as much as possible not to damage the structure that we're looking at. So visual inspection, reinforcement surveys, and integrity surveys, in situ quality of the concrete and the foundations. And this can all be done non-destructively. So you can have a good visual inspection on a foundation, preferably by a very experienced engineer. He has an idea what he's looking for. We can do cover and ground penetrating radar on these foundations. This one here was where during construction, the actual shutter failed, concrete had poured out. they put it back in. So the idea was we wanted to do some structural integrity testing. So here you can see here, apologies. So here's structural impact echo testing, and we'll look at that later on. And then finally, something that I find is very, very useful to give us an indication of the real quality of the concrete is permeability. If the concrete is very impermeable, it's very difficult for liquid and other aggressive substances to get into reinforcement or out the concrete. And again, it's something that can be tested non-destructively. Ultrasonics then, well, I suppose we'll look at visual inspections first. Again, when we're on site, we want to check before we actually dig down, ground penetrating radar, let's see if we find any obvious defects that we might want to target. As soon as we open up the foundations, we're looking at the concrete surface, we're looking at the edge of it all possible. Is it smooth? Is it hard? Is there obvious deterioration on it? And here's sort of an image of an acid-attacked concrete. This is not a foundation from a turbine, it's from a different wall. But again, you can see very, very quickly if the surface has been eaten away by some sort of chemical or other attack. And then obviously, guys, if there's any kind of corrosion nodules sitting on the surface, again, it's your spidey senses are tingling. You kind of feel for what might actually be happening on the foundations. Again, remember, you're digging this out for the first time. You don't know what its condition is. And obviously, if you see cracking, the location of cracking really gives an indication of what might be happening. Overloading, delamination due to carbonation or chlorides, acid attack, sulfate attack. There could be a multitude of different reasons why cracking may occur in the concrete. And obviously, crack microscopes can be used to measure the widths. You can actually put sensors in now that can ultimately monitor the movement of those cracks over a period of time. But one of the big jumps forward, I think, from a crack point of view, is that now we can now image cracks very, very clearly. So we can see whether it's a single line crack, there's not much kind of branching out of it. We can actually very carefully measure the crack width. We can go back to that location and redo it. But ultimately, if we are getting a mainline crack, where there's a lot of tearing and sub-branching from that crack, again, that's giving us an indication of what's driving the deterioration in the concrete. So even just from simple cracking, we can gather an awful lot of information if we use the right techniques and right tools. And then what we'll do is we'll move on to reinforcement. These structures, as you guys know, are very heavily reinforced. So the old-fashioned simple cover meters are not going to actually cut it anymore. We need to be going to the more kind of a high-end, the likes of the Ferroscan PS300, PS1000, or ground penetrating radar, where you can get very clean, crisp images from the reinforcement beneath the surface. Again, this is non-destructive, and with a little bit of post-processing, we can actually kind of estimate rebar diameter, and again, relating that back to the design information. And then we can actually kind of get a lot of information. We can get spacing, we can get cover. So again, non-destructively from a reinforcement point of view, a lot of information, but up near the can, the reinforcement is incredibly dense. And really and truly, even those cover meters struggle. So this is where you want to be looking at something like ground penetrating radar. And this is the imaging you're getting from ground penetrating radar. Here you can actually see where you've got lapping of the reinforcement. You can see the way it's slightly off center. So the ground penetrating radar really adds to that imaging of placement of the reinforcement. Not necessarily cover, but definitely of the placement of the reinforcement. And again, there's lots of different systems, ProSec, GSSI, Hilti, they all have variations on a theme. This is just one. But ultimately, whatever system you want to get, you've got to think of it from a structural point of view. Where is the reinforcement? What condition is it in? And this is the type of information we want to be presenting to the structural engineers who are going to do the assessment after we're finished. So when that's finished, then we would move on to corrosion. Obviously, a big part of this, because these are typically buried in quite harsh environments, a lot of moisture. So typically, we would look first off would be the half cell potential method, and this is on a wind farm base where you take out your grid. You would actually then you'd have your breakout, which we'll look at in a minute. We'll make electrical connections to reinforcement, and we could measure the actual risk of active corrosion on your reinforcement. And typically the risk comes in several different categories. More negative than -350 on a copper sulfate half cell would certainly indicate more than 90% probability that active corrosion is ongoing. And you'd have to take steps then to try to reduce that. So that's an indication of risk. Then we'll have resistivity. Resistivity is a very simple method, but it is more about the concrete's ability to allow corrosion to occur. When that's done, then I think the biggest jump forward here will be the connectionless measurement of corrosion rates. So now we have the ability to look at the corrosion and estimate how fast that rebar is losing its cross-section area per year non-destructively. And that's going to be a simple system called the ICOR from Geotech. But ultimately, we can create heat maps or contour maps of where we want to look at from a corrosion point of view. And then we get an idea very, very quickly. We have rates per year, and then we've got active or passive to passive low rates all the way to severe rates. So again, we're getting an indication of how severe the corrosion is on those reinforcement foundations. And look, I've said here that they're expert systems. There is some problems and limitations with these systems, and you've got to be very aware of them. So next thing we'll do is stress wave technology. This is a massive jump forward in how we look at the integrity, the in-situ integrity of our concrete structures. The first one then would be impulse response. This is a super tool, non-destructively, to rapidly assess the in-situ condition of your structure. So it's not going to tell you what's wrong, but it certainly will give you an indication of where something is wrong. And what you would typically do is you grid out the area, typically around 500, 600, 700 millimeter squares, grid points, and then basically you have a two-man operation. One is impacting the surface, the other has a transducer, and the other guy is actually monitoring the wave response. From that, then you would typically come up with an actual mobility plot. And that mobility plot can be interpreted, as we see here, whether something is in good condition, which is a low mobility, or a very high mobility, or a very early peak from a void ratio. These are all indications of what might be wrong in your concrete structure. And you've got to then do your intrusive investigations, which we'll deal with in a minute. The next, and you can see very quickly what you can actually put down from your impact echo or from your impulse response. The idea will be is, where do we have to target for intrusive investigations? It's not guessing. The next thing is pulse echo tomography. Again, this is on a wind turbine foundation. And ultimately what we're trying to do is we're sending out a multitude of high frequency ultrasonic pulses, throw it like a cat, throw it out, and then the rest of them are all catching it. And what it actually does is it creates a very high-end ultrasonic cross-section image of your structure. So you can see here taken from a wind turbine foundation. You can see the base at about 800 millimeters below the surface. You can see where the reinforcement is. And what's good here is there is no other defects through the actual section at that point, which is exactly what we see. I think that's reinforcement there around 650 down. So ultimately, you're not seeing any heavy reflections. So you have a good indication as to whether your structure or your foundation is performing. One nice thing about this system is we can actually look at the S wave or the shear wave velocities, and that will also give us an indication or classification for the condition of the concrete. And what you don't want to see is the one image in this that's not belong to me is this. All right, we don't want to find large, big voids below the surface on our foundations. And something like a pulse echo tomography using the mirror system will actually be very, very good to non-destructively give you a real indication as to the condition of your foundation without breaking the surface. Impact echo testing is very, very similar. Again, you have a computer-based software. You impact the surface with a very small impactor or varying size of impactor. You have a transducer. It uses the software. The problem with impact echo, what I always find is you got to know the answer. You got to know the frequency before you actually kind of to do the test. So it is really an expert system, but it's an excellent system, mathematical based. So it doesn't really give you any imaging. It's purely numbers based. So you have to know the numbers before you do the test, but it does work and it will find voids below the surface. It's pinpoint system, one phase only, much, much smaller, much more focused, but a very accurate system if used properly. So what we'll do then is we'll move on to the next system, permeability methods. And as I've explained, and this is a very quick synopsis, a quick run through, there's many different forms of permeability. Two that we use regularly enough would be the German instruments, GWT. This actually under pressure forces water into the actual concrete and actually measures the rate of water penetration. So if you had, and it's really, really good for comparative testing, if you've repaired concrete, if you've coated concrete, if you're doing the GWT penetration test before and afterwards, you'll see how effective the coating system or the repairs have been. Again, largely non-destructive. You have to drill 2 little holes to hold it into place, obviously. But it's a really simple test. It takes about 15, 20 minutes to do. You get a really good indication of how good the resistance of your concrete is to water penetration. As I've said here, this is the air permeability test kit from ProSec at the Turbine system. Again, better probably suited to drier concrete. So maybe when concrete is wet and low surface, it's not as easy to do it. But this will actually force and suck air into the actual vacuum chambers. And based on that, then it actually gives you a real indication of that, particularly that surface creep, that what really kind of defends against your penetration of your aggressive substances. And it gives you an idea from very bad to very good quality concrete. And one nice thing was in Switzerland, they came up with SIA 262 Part 1 back in 2003. And from that, then they looked at what sort of permeability KT values would equate to the various different exposure environments from EN206. And again, we were able to get values that relates back to 0.5 or less would be very severe frost, severe chloride environments. And that's kind of given us an indication of what sort of environment your concrete should be in. And going back to your design drawings, what was the concrete originally designed for? So you kind of can link it all together very, very quick with permeability methods. So the next one then, so that's the end of the NDT methods. From that then, we have a really good idea where we want to do partially destructive. And partially destructive inevitably ends up as diamond coring. And there's lots of different rigs. This is one we were actually drilling through at just beside Cannes, extremely heavily reinforced. We did our best not to cut reinforcement. And look, we did nick an odd bar here and there, but the hydraulic rig is much better. It's a really, really heavy, very, very strong rig for heavily reinforced concretes. Then you actually just have the electric systems. And again, the key here is to mark out the reinforcement to minimize the chance that you will actually cut reinforcement. You can see there where you want to core, the horizontal bar, the vertical bars are all marked out. Then in the cores, if you take out, use the core hole. Give yourself an indication of what the likelihood of the binder condition. Does it look like the aggregates are well distributed? What sort of aggregates? Are we looking at 20 mil, 10 mil? What's in there? And is there any obvious voiding or anything that could be wrong? When we take the core out, again, we'll use it. But the core is particularly useful for two big, or several things, but for two big items. Compressive strength testing, and this is what I love, petrography. And this is what I was saying back when I looked at the Concrete Bridge Development Group schedule of tests. This is taken not from an actual wind farm. This is taken from a wall that was heavily corroded due to acid attack. But you can actually see where you've got the corroded binder, you've got the carbonated there and uncarbonated there. So very quickly now we know the depth of deterioration in our concrete. And if we've got to remove that contaminated concrete, it's very specific to tell the contractor it's X depth. So big time, very, very useful for those for cores, and obviously compressive strength. This is something that we deal with constantly, checking compressive strength. There is a new standard, or a relatively new standard in Ireland, in Europe, ISEN 13791, and it's very specific methodologies for compressive strength analysis. So it's no longer just take a core and that's the strength. That's not really how it works anymore. The actual standard is very specific how you determine your characteristic in situ compressive strengths. And there are charts available for various different types and various volumes of concrete in structures. So then we move on to the other partially destructive methods, breakouts. And this is something that was done on a wind farm where you would actually locate your reinforcement. When it's shallow, where the reinforcement is shallow, you break it out by hand. Where the reinforcement is deep, you might want to core it. Again, where the actual testing that you would have done previously, you know where the reinforcement is, you know what depth it is. So when you're coring or breaking out, you're not damaging in situ reinforcement. You can very quickly see the type of reinforcement, the actual cover, the condition of the reinforcement, the diameter of the reinforcement. So you get a lot of information. And what's really nice is you can actually then kind of take the material away from chemical analysis. You can get cement content analysis and other chemical tests. And this is where we've done on one of the wind farms with UCD, where there were strain gauges installed on the reinforcement before the actual hole was repaired. So again, you can get a lot of information by actually doubling up on various different types of tests that you might want to do. So then in situ sampling, all right, the purpose, we want to learn a lot about our concretes from the samples. So if there's crack depth, if it's carbonated, chloride, cement, sulfates, alkalis, petrography, we can use these samples. This is one that we took from, again, not a wind farm because we didn't find full depth cracking, but you can see 500 millimeter deep cracking in that structure. So very, very quickly, you know you've got a problem. And when we looked at petrography, the problem is deeper in again than that. So, you know, deep structures, even though they're large and heavy structures, they do crack. You can actually see in this one, it's a core that we took out. The reinforcement is here. You can actually see the level of carbonation, and you can actually see the depth of carbonation. Carbonation typically reduces the active pH in the concrete from around 12.5 down to less than 9. That gets rid of that local passivity that you would have protecting the reinforcement, and then would allow for much faster corrosion to occur in the reinforcement. So you can get a lot of information very, very quickly. Your sampling rate will often depend on the variability. How much are you going to get, and what are you likely to find? The accuracy, the time, how destructive it is, and obviously cost is a huge factor in all this. And then when you actually sit down and you have all that information beside you, you have the visual info or the desktop information. Is what you actually saw the same? Is it roughly, thereabouts? Is when we look at visuals, is there cracking? Is there something abnormal happening on the surface? When we look at then the reinforcement surveys, are you losing a lot of sectional area because of corrosion, high corrosion rates? Have you got a problem with uniformity? There's the differences in the concrete. Is there an issue with hidden voids or hidden defects within it? Is the reinforcement where it's supposed to be? Is the compressive strength where it's supposed to be? And then very important things. And when we link it back to the original designs, cement content, minimum cover, compressive strength, these all feed back into EN 206, the exposure environments, and what it was originally designed for. So what it was originally designed for, you still have it today. So there's a lot of information. This is just something that we done a little while ago, where we could cracking, if the reinforcement is exposed in those cracks, then it's exposed to water, it's exposed to oxygen, and any other contaminated material that could affect the corrosion rate in the reinforcement. And this is just some reinforcement from a sample we did a few years back, heavily corroded due to chlorides, and you can see the chlorides have eaten away the steel. So it isn't just sort of something that might happen. And this is in Ireland, by the way. This is actually in Ireland. Chlorides can be a major problem if we don't know what's going on. And obviously, we would like to profile it as part of our evaluation and estimate then how likely corrosion due to chlorides or something else will happen over time. So, and look at guys, I suppose just before I say thank you, Infrastruct has joined with MetLab, and now we have the ability not just to take on concrete, but it's also a lot of metals and plastics. So MetLab going forward, hopefully we'll help you with not just below ground, but also the above ground testing. Thank you very much.